Engineers do not gasp. That is a professional norm so deeply embedded in the culture of powertrain development that it survives even the most dramatic test results. You look at the number, you check the methodology, you run the verification, you compare against the benchmark. And if the number is extraordinary, you say something measured and calibrated, like that is a significant result or that warrants further analysis. In the spring of 2024, when BYD's fifth generation DM hybrid system posted a thermal efficiency figure of 46.6% on an independently verified test cycle, the measured and calibrated response lasted approximately 48 hours. After that, the engineers started saying what they actually thought. What they actually thought was that the number should not exist. That 30 years of hybrid powertrain development by Toyota, Honda, Bosch, and every serious European and American powertrain program had established a ceiling that this number had gone through cleanly, without apparent effort, and without anyone in the Western automotive industry seeing it coming. The record that wasn't supposed to fall. Thermal efficiency is the number that matters. It measures what fraction of the chemical energy stored in fuel is actually converted into useful mechanical work by an engine, as opposed to being lost as heat through the exhaust, the cooling system, and friction throughout the mechanical drivetrain. A perfectly efficient engine would convert 100% of fuel energy into work. The laws of thermodynamics make this impossible in principle, and the engineering realities of real combustion make it impossible in practice by a substantial margin. The question for powertrain engineers is always the same. How close to the theoretical maximum can you get with real materials, real fuels, real combustion chemistry, and real manufacturing constraints? For most of automotive history, the answer was discouraging. Early gasoline engines achieved thermal efficiencies around 15 to 20%. That meant 80 to 85% of the energy in every liter of fuel was being thrown away as heat. Decades of engineering improvement pushed that figure gradually upward. By the 1990s, well-designed, naturally aspirated gasoline engines were reaching around 35% peak thermal efficiency. By the 2000s, Toyota's hybrid optimized engines, designed to run in a narrow band of operating conditions where efficiency is maximized, were approaching 38 to 40%. This was considered extraordinary. The Atkinson cycle engine in Toyota's Prius, which became the global benchmark for hybrid powertrain efficiency, was regarded by competitors and independent analysts alike as representing very close to what gasoline combustion could practically achieve. Toyota's third-generation hybrid system, deployed in the Prius and across its broader hybrid lineup, achieved a peak thermal efficiency of 41%. This was announced with considerable fanfare in 2017 and was widely described by automotive media and engineering publications as a landmark achievement. Several respected powertrain engineers stated publicly that thermal efficiency above 42 or 43% for a production gasoline engine was not a realistic near-term engineering goal. The thermodynamic constraints, the materials limitations, the combustion instability issues that emerge at very high compression ratios and very lean fuel-air mixtures, all of these converged on a practical ceiling that the engineering consensus placed somewhere in the low 40s. Getting meaningfully above that ceiling, the consensus said, would require either a fundamental change in fuel chemistry or engineering advances that were not on any visible near-term roadmap. The consensus was wrong, and the party that proved it wrong was not Toyota. It was not Honda. It was not Bosch or Continental or any of the German engineering firms that have dominated internal combustion development for a century. It was a Chinese electric vehicle company that most Western automotive engineers had, until relatively recently, regarded primarily as a battery manufacturer that happened to also assemble cars. What China actually built BYD's fifth-generation DM hybrid system is worth examining with the same careful attention that the Huawei Kirin chip received after its teardown revealed something the industry said was impossible. The engine at the heart of the system is a 1.5-liter naturally aspirated gasoline unit designated the BYD EA series, developed specifically for hybrid operation and optimized for peak efficiency over a narrower operating range than a conventional engine that must perform across all driving conditions. The headline figure is 46.6% peak thermal efficiency. This number has been independently verified by third-party testing organizations and is not a laboratory curiosity achieved under conditions that bear no relationship to real-world operation. It was achieved under test protocols that the automotive engineering community accepts as representative of genuine powertrain capability. It is the highest peak thermal efficiency figure ever recorded for a mass production gasoline engine. It is not close to the previous record in the way that records often fall by incremental margins. It clears the previous best-in-class figure by a meaningful gap that reflects not incremental refinement, but a qualitative step in engineering approach. The system context matters as much as the engine number. BYD's fifth-generation DM architecture is a dedicated hybrid architecture, meaning it was designed from a clean sheet as a hybrid system rather than adapted from an existing conventional powertrain. The combustion engine in a dedicated hybrid does not need to operate efficiently across the full range of speeds and loads that a conventional engine must handle, because electric motors fill in at the operating conditions where the engine would otherwise be inefficient. This freedom to optimize for a narrow efficiency peak rather than a broad operating range is not unique to BYD. Toyota exploits the same principle. Honda exploits it. Every serious hybrid architecture exploits it. What is unique is how far BYD pushed the optimization using a combination of engineering innovations that the Western hybrid industry was either not pursuing at the same intensity or had not yet combined in the same architecture. The production reality is equally significant. This is not a technology demonstrator. It is not a concept engine that will take 5 years to reach production readiness. The fifth generation DM system is already in mass production, already powering BYD's Chin-L, Han, and Tang hybrid models, already being delivered to customers in China at volumes that make it one of the highest production hybrid powertrains in the world by unit count. The engineering achievement is embedded in products that are being sold today. That is what separates it from a laboratory result. The engineering that made it possible. The 46.6% figure did not emerge from a single breakthrough. It is the product of multiple simultaneous innovations in combustion engineering, thermal management, and mechanical design that individually would each have delivered modest improvements and that together produced a result that surprised the industry. Understanding what China actually did requires going through these innovations one by one. Extreme Atkinson cycle operation is the foundation. The Atkinson cycle extends the expansion stroke of the engine relative to the compression stroke, allowing the combustion gases to do more work before being exhausted. This improves efficiency, but reduces power density, which is why it is only practical in hybrid applications where the electric motor compensates for the power deficit. BYD pushed the Atkinson cycle ratio further than any previous production engine, achieving an effective compression ratio of approximately 15:1 while maintaining stable combustion at conditions where conventional engines would experience knock, the uncontrolled detonation that damages engines and forces engineers to back off compression ratio and efficiency. Laser ignition technology contributed significantly. Conventional spark plug ignition initiates combustion at a single point and relies on the flame front, propagating outward through the fuel-air mixture. Laser ignition can initiate combustion simultaneously at multiple points within the combustion chamber, producing a faster and more complete burn that extracts more energy from each combustion event before the exhaust valve opens. Faster burn rates also reduce the tendency toward knock at high compression ratios, which is the key reason laser ignition enables the extreme Atkinson cycle ratios that the EA engine uses. This combination, laser ignition enabling higher compression ratios, enabling more extreme Atkinson cycle expansion, is central to the efficiency story. Supercooled exhaust gas recirculation, EGR, is the third major innovation. EGR involves routing a portion of exhaust gas back into the intake charge, diluting the fuel-air mixture in ways that reduce peak combustion temperatures, decrease pumping losses, and suppress knock tendency. Cooling the recirculated exhaust gas before reintroducing it into the intake amplifies these benefits by increasing the density of the diluted charge and further reducing combustion temperatures. BYD's implementation of cooled EGR operates at dilution rates and temperatures that push beyond what previous production hybrid engines have demonstrated, and the combination with laser ignition allows stable combustion at these extreme dilution levels where a conventional ignition system would produce misfire. Ultra-low friction mechanical design accounts for the remaining efficiency gains, reduced piston ring tension, diamond-like carbon coatings on critical wear surfaces, offset crankshaft geometry that reduces piston side forces during the power stroke, electric oil pump and water pump operation that eliminates the parasitic losses from belt-driven accessories, variable displacement oil pump that delivers only the pressure and volume actually required at each operating condition, rather than pumping continuously at maximum capacity. None of these innovations is individually dramatic. Together, they recover efficiency that conventional engine design leaves on the table through accumulated mechanical friction. Every percentage point of friction loss eliminated contributes directly to the thermal efficiency figure. BYD eliminated more of them simultaneously than any previous production engine program. The thermal management system that keeps all of these elements operating in their optimal temperature windows is itself a significant engineering achievement. A dedicated coolant circuit for the EGR cooler, separate from the main engine cooling circuit, allows independent temperature control that maximizes EGR effectiveness across all operating conditions. Active thermal management of the cylinder head and cylinder block maintains the temperature gradients that minimize friction while maximizing combustion efficiency. The engineering sophistication of the thermal management system is, in several respects, as impressive as the combustion innovations it supports, the numbers that ended the debate. Specific numbers matter. They are what transforms an engineering announcement into an industry reckoning. The BYD 5th generation DM system has generated enough independently verified data to make the debate about whether the achievement is real essentially over. The 46.6% peak thermal efficiency figure was verified by China Automotive Engineering Research Institute testing conducted under protocols that the international automotive engineering community accepts. This is not a number that BYD measured itself on its own equipment under its own conditions and announced at a press conference. Independent verification changes the evidentiary weight of the claim substantially. Toyota's 41% figure, the previous benchmark, was also independently verified under comparable protocols. The comparison is valid. The gap is real. It is 5.6 percentage points, which in thermal efficiency terms is an enormous margin. The entire improvement in gasoline engine efficiency from the early hybrid era to Toyota's 41% record took roughly 15 years of sustained engineering development. BYD crossed a larger gap in a shorter time, starting from a position that Western analysts did not regard as leading edge. Full system efficiency in real-world hybrid operation is arguably more important than peak engine efficiency for understanding consumer and commercial value. A peak efficiency number is achieved only at a specific, narrow operating point. A hybrid powertrain must manage the engine across a range of conditions, and how efficiently it does this across the full driving cycle determines fuel consumption in the real world. BYD's system-level fuel consumption figures on Chinese and European test cycles consistently produce results that compare favorably against Toyota's best hybrid systems, despite Toyota's 30-year head start in hybrid system optimization. In the Chin L, BYD's most efficiency-focused hybrid sedan, the WLTC combined cycle fuel consumption figure, sits at approximately 4.3 liters per 100 kilometers. Toyota's comparable Corolla hybrid, using Toyota's latest hybrid system, achieves approximately 4.6 liters per 100 kilometers on the same test cycle. BYD is ahead. Not by a dramatic margin, ahead. The production cost dimension of the numbers is where the industry implications become most stark. BYD's vertical integration, which extends through battery cells, electric motors, power electronics, and now into the advanced engine components required for fifth-generation DM operation, allows it to produce this system at a cost that European and American automotive engineers who have studied the question describe consistently and with visible discomfort as something they cannot currently match. A technology that is simultaneously more efficient and cheaper to manufacture than the competition's best product is not a temporary advantage. It is a structural one. This didn't come from nowhere. China's ability to produce a fuel efficiency world record in 2024 rests on a foundation of powertrain research investment that began accumulating seriousness roughly a decade ago, and that received almost no attention in Western automotive media until the record existed. The National Key Research and Development Program, which channels state funding into priority technology areas identified by China's Ministry of Science and Technology, designated advanced internal combustion engine efficiency as a priority research area in 2015. This designation came with funding commitments, institutional coordination mechanisms, and performance targets that focused the efforts of Chinese university research programs, state-owned automotive research institutes, and private automotive companies around a common set of efficiency goals. The Tianjin University Internal Combustion Engine Laboratory, one of China's premier powertrain research institutions, received sustained funding for combustion optimization research that directly fed into the technical approaches BYD ultimately commercialized. Tsinghua University's Automotive Engineering Department contributed research on lean combustion stability and ignition system optimization that is directly relevant to the laser ignition approach BYD deployed. The research pipeline between Chinese universities and Chinese automotive companies is shorter and more deliberately managed than equivalent pipelines in the United States and Europe. That pipeline delivered. BYD's own internal research investment in powertrain engineering accelerated sharply from 2018 onward, as the company recognized that its hybrid strategy required competitive combustion engine technology, not just competitive battery technology. Wang Chuanfu, BYD's founder, made the decision to build world-class internal combustion engine capability in-house at a time when many Western observers were characterizing BYD primarily as a battery company that bolted engines onto its platforms as a concession to market reality. That characterization missed what BYD was actually building. The EA Engine series, which culminated in the 46.6% achievement, represents years of internal development investment by an engineering team that grew from modest beginnings to several thousand powertrain engineers working on problems that the Western automotive industry did not believe Chinese companies were pursuing at serious depth. What Toyota and Honda are actually thinking. Toyota's response to BYD's thermal efficiency record has been publicly measured and privately more urgent than the public statements suggest. Toyota built its global hybrid reputation on the Prius and on the engineering leadership that the Prius represented. The THS, Toyota Hybrid System, is the most deployed hybrid architecture in the world by a substantial margin. Toyota has sold over 20 million hybrid vehicles powered by this technology. The brand identity that Toyota has constructed around hybrid leadership is not a minor marketing asset. It is a central element of how the company differentiates itself in a global automotive market that is rapidly commoditizing across multiple vehicle categories. a Chinese competitor holding the fuel efficiency world record with a mass production hybrid system that is also cheaper to manufacture than Toyota's equivalent, is a direct challenge to the core of that brand identity. Toyota's engineering teams are not dismissing the BYD achievement. They are studying it intensively because the combination of innovations BYD deployed, particularly the laser ignition and extreme EGR approach, represents a technical path that Toyota's own research programs explored but did not prioritize for production deployment on the same timeline. The question Toyota engineers are working through is not whether the BYD result is real. The question is how quickly they can match or exceed it. Toyota's response is already visible in its announced next-generation hybrid system roadmap. The company has publicly committed to achieving greater than 50% peak thermal efficiency in its next-generation hybrid engine, a target that would have seemed implausibly ambitious 18 months ago, and that is now being framed explicitly as a response to the competitive landscape that BYD's achievement has created. Whether Toyota reaches 50% before BYD does is one of the most consequential engineering races currently underway in the global automotive industry. It is receiving far less coverage than it deserves. Honda's hybrid technology, marketed under the iMMD brand, has also been a genuine engineering achievement that achieved strong efficiency results in Honda's Accord and CR-V hybrid models. Honda's engineering teams have been more publicly forthcoming about the significance of BYD's achievement than Toyota's, perhaps because Honda has less brand identity capital invested in the specific claim of hybrid technology leadership. Honda's response has involved accelerating its own next-generation combustion optimization program and publicly acknowledging that the Chinese automotive industry's engineering capability has advanced to a level that demands to be taken seriously as a technology peer rather than a cost reduction competitor. The broader industry disruption. Every major automaker with a significant hybrid program is reassessing its powertrain technology roadmap. The implications extend well beyond Japan's hybrid specialists. German automakers have the most complex response to manage. Volkswagen, BMW, and Mercedes-Benz built global reputations on powertrain engineering excellence. The diesel engine, the twin-turbocharged gasoline engine, the sophisticated automatic transmission, these are areas where German engineering has genuinely led the world for decades and where the engineering culture is deeply invested in that leadership as a professional and commercial identity. Having a Chinese competitor hold the fuel efficiency world record is not a neutral data point for companies whose differentiation rests substantially on powertrain engineering superiority. It is a challenge to an identity, and identity challenges tend to produce more urgent responses than purely commercial ones. Volkswagen's situation is particularly acute. The company is simultaneously navigating the transition to battery electric vehicles, managing overcapacity in its European manufacturing base, and competing in the Chinese market against BYD and other domestic automakers offering comparable or superior technology at lower price points. The fifth generation DM system makes the hybrid segment of that Chinese competition significantly harder because it removes the technology quality argument German brands used to justify their price premium. If BYD has better hybrid efficiency than Volkswagen's equivalent system, the price premium becomes very difficult to defend to Chinese consumers who are comparing specifications with increasing sophistication and diminishing patience for premium pricing that cannot be technically justified. American automotive manufacturers have largely retreated from hybrid technology leadership in favor of full battery electric vehicle development. The BYD record lands in a different strategic context for American automakers because the American hybrid market is smaller and the strategic bet has been more explicitly on full electrification. But the global export market implications are identical for all of them. A Chinese hybrid system measurably more efficient than any Western alternative at lower production cost is a formidable export product in markets where hybrid vehicles remain the dominant electrification pathway for the foreseeable future. That is most of the world outside Western Europe and North America. The hybrid as strategic weapon fuel efficiency leadership is not simply an engineering achievement. In the context of China's automotive export strategy, it is a market access tool, a trade policy instrument, and a geopolitical positioning asset operating on multiple levels simultaneously. China became the world's largest automotive exporter by volume in 2023, surpassing Japan and Germany for the first time. The vehicles driving that export growth are predominantly new energy vehicles, including both battery electric vehicles and plug-in hybrids. The fifth generation DM system is the powertrain technology that makes BYD's plug-in hybrid exports competitive in markets where pure electric vehicles face range anxiety barriers, charging infrastructure limitations, or strong consumer preference for conventional refueling convenience. The markets where Chinese automotive exports are growing most rapidly, Southeast Asia, Latin America, the Middle East, Eastern Europe, are precisely the markets where infrastructure and consumer conditions favor plug-in hybrid technology over pure electric vehicles for the near and medium term. A Chinese plug-in hybrid with world record fuel efficiency, competitive pricing, and increasingly capable software and connectivity features is an exceptionally strong product for these markets. The efficiency record is not just a bragging right. It is a sales argument that connects directly to fuel costs in markets where those costs are high relative to income. The European Union's tariffs on Chinese electric vehicles, imposed in 2024, apply specifically to battery electric vehicles and not to plug-in hybrids in the same way. BYD's fifth generation DM system produces vehicles classified as plug-in hybrids that navigate around the tariff structure in ways European policymakers are now examining with considerable urgency. The efficiency record makes those plug-in hybrid products even more competitive in European markets at the moment when European policymakers thought they had constructed a protective barrier. The barrier has a gap in it. The gap is shaped exactly like a 46.6% efficient hybrid powertrain. Where this goes next. The 46.6% figure is not a destination. It is a point on a trajectory that is still climbing, built by an engineering team that is already working on what comes next. BYD has publicly indicated that its next-generation powertrain development targets thermal efficiency above 48%. This target, which would have seemed science fiction in 2020, is now a credible engineering goal given the demonstrated capability of the team that reached 46.6%. The technical paths toward 48% involve pushing each innovation in the fifth generation DM system further along its development curve, higher EGR dilution rates enabled by improved ignition energy delivery, further combustion chamber geometry optimization using computational fluid dynamics tools that are themselves improving, advanced cylinder wall coatings reducing heat transfer losses beyond what current materials allow, variable compression ratio mechanisms adapting engine geometry dynamically to different operating conditions in real time. The 50% thermal efficiency barrier is the number that powertrain engineers now discuss the way battery researchers discuss energy densities above 500 watt-hours per kilogram. It is the threshold that would represent a qualitative step beyond anything previously achieved, requiring solutions to engineering challenges that do not yet have fully worked out answers, and that is now being discussed as a plausible medium-term target rather than a distant theoretical aspiration. BYD's 46.6% has moved 50% from the category of impossible to the category of very hard. In engineering terms, those are very different categories. Very hard gets done. Impossible provides cover for not trying. The broader trajectory is the context in which the efficiency record must be understood. A decade ago, Chinese automotive engineering was regarded as a step behind global leaders in every powertrain category. 5 years ago, Chinese battery technology had emerged as genuinely world-leading. 3 years ago, Chinese electric motor and power electronics technology had reached global competitiveness. Now, Chinese combustion engine efficiency holds the world record. The pattern is consistent, the direction is consistent, the pace is consistent. Nobody paying attention to the pattern should be surprised by what comes next. The world record fell quietly, without the buildup that usually precedes a landmark result, without the anticipatory coverage that would have prepared the industry. It fell the way genuinely disruptive developments tend to fall, suddenly visible in retrospect and impossible to unsee once seen. In Tianjin and Shenzhen and the research laboratories of a dozen Chinese universities, the next record is already being built. It will not announce itself before it arrives either.